All right. Making progress. Chat. I really like this chat. Okay. Okay, how are we doing today? Happy Tuesday? Not Monday. I can always say that in this class. It's really nice. It's not Monday. And everybody got their homework done for chapter 6, right? So I pulled grades from my lab and mastery this morning because chapter 6 was due last night. So I pulled this morning. So all of your grades from my lab and mastery should have ported over into Moodle. So nobody should be at like a half grade, because sometimes that happens if I pull in the middle of an assignment. So I tried to not open the next one until I pulled grades. So your chapter 7 is now open since I pulled grades this morning. Okay? Yeah? Good. How much time we got? 2 minutes. And I forgot my jacket today. I'm gonna freeze. I'm really gonna freeze, I know. Actually see me. Cold. All right, we're pretty close. Yeah, I want y'all joke of the day. Okay, you ready? Did you hear about the mathematician who's afraid of negative numbers? You know he'll stop at nothing to avoid them. Takes a minute for that one to set in. He'll stop at nothing to avoid negative numbers. Poor mathematician. Should not be a mathematician. All right, so just to kind of review things, our next exam is next Tuesday, right? Next Tuesday, so 1 week from today. What is it on? 5, 6, and 7. It is on 5, 6, and 7. Homework 6th grade, homework 6 was due last night. Homework 7 is now posted. That's due next Monday at 9 p.m., right? And then I've posted all the videos for chapter 7. Now, sections 1 and 2 for chapter 7 were kind of long. And so I integrated a couple of questions into the lecture and then just made the in-class problems from that kind of optional, just because I felt like it was a lot already. But if you need more practice with that, you can go and watch those videos. And then, oh yeah, for chapter 7, 4, and 5, sections 4 and 5, I put them together in a video. And I have to apologize because I was doing the lecture and I got to the point where I was switching over to the problems and I didn't share it correctly. So for the first like 3 problems, I'm talking and all you get is black screen. But at some point I realize it and then I go back and I show you everything. So I'm sorry, but you know, technology happens. So you get it all. Just realize I know the screen is blank and it will be okay. I will realize it in the video and I'll go back and fix it. So don't give up on the video, even though it's a black screen. Okay, so we're gonna start with some, oh, I forgot to put up the attendance slide. Sorry about that. So we're going to start with a little review on chapter 6. We have a few quick clicker questions. Maybe. There it is. Okay, so let's do our attendance real fast. Doing the wrong thing. Yes. Okay, so go ahead and click in on your attendance. I'll give y'all a minute. And then I've got chapter 6 clicker questions for you. So it's kind of a review. So I'll give y'all a minute or two to get clicked in. Okay, I'm gonna go ahead and close this because we don't need that anymore. Ooh, make that big, maybe. Okay, and that was the last one we did. We did this one, chiral centers. I think that was the last one we did, pretty sure. Okay. All right. I'm going to switch over from attendance to clicker questions. All right. So here's our very first one. The structure of sorbose is shown below. Select the correct classification. So select the correct classification. And remember, I'm giving you a minute and a half. Ten seconds. Jaden, try turning your device off and back on again. Okay, so what do we have in this structure? What's right here? Is it a ketone or is it an aldehyde? It's a ketone. How do you know it's a ketone? We got two things, lock and a key, right? 1, 2. So that's a ketone. So we can X out all these ones with an aldehyde. Now what? Now we have to know, is it hexose or is it pentose? So let's count our carbons. 1, 2, 3, 4, 5, 6. What's 6? Hexose, so we can get rid of that one. Now, is it D or is it L? So we look at the hydroxyl that's farthest away from our carboxyl, and it is on the what? On the left, so it must be L-ketohexose. So it should have been C. So most of y'all said either L or D, so you got to remember, L is left. L is left. All right. Okay, so try this one. And Jade, did you get your clicker to work? Yeah, okay. Ten seconds. Okay, ketone or aldehyde? This is our carbonyl carbon, ketone or aldehyde? 2, so ketone, so we can cross out our aldehydes. How many carbons? 6 carbons. Okay, so that must be a hexose. Why didn't we have to put L or D? Is it L or D? Well, what is it on here? Is it an L or D? It's a D because we're on the right. And so if it's a D, do we have to write the D? No, it's understood. If we don't list anything, it is understood as D. So you don't have to put it. Okay, so good. Good. All right. Okay, so now we've got to talk about our beta, our beta or alpha glycosidic bonds, right? So go ahead and look at the molecule and try to identify what is the glycosidic linkage between these two monosaccharides. Ten seconds. Okay. So what do we know that we have? First, you're going to find what kind of carbon? Your anomeric carbon. So this is the anomeric carbon that's participating in the glycosidic bond, right? Okay, what number carbon is that? That is carbon 1. And is that in the alpha or beta orientation? It's cis, so it's beta. Okay, so we can eliminate all of our alphas, right? Now we have to go in and count our other one. 1, 2, 3, 4. So this must be a beta 1, 4. So that would be A. Good. Oh, awesome, y'all. All right. Now, here's one about sucrose. Tell me the correct statement about sucrose. 10 seconds. Okay, so sucrose, what do we know? Is it a disaccharide, monosaccharide, or oligosaccharide? Disaccharide, so we can eliminate these. Now you just need to figure out what does it contain. And it is a fructose and a glucose. So what did y'all say? Oh, awesome. I'm liking the scores on these clicker questions. All right, so tell me, why are oligosaccharides important? Oh, 5 seconds, sorry. I'll give you all 10. So it's at 1:35. Okay. So tell me, what's an oligosaccharide? How many sugars? 3 to 9. Okay, so that's really important to answer this. So oligosaccharides are the main structural materials in plants. True or false? What is the main structural? I know you know the name of it. What are starches composed of? Cellulose? Is cellulose an oligosaccharide? What is it? It's a polysaccharide, right? Polysaccharides can be 10 to 20, 10 to 20, 10 to however many long, right? Doesn't matter. So they're not, so this is a polysaccharide. How about oligosaccharides are the major energy source for plants and animals? True or false? False, they're polysaccharides. Oligosaccharides are a form of energy storage for animals. False, they're poly, right? They're all polysaccharides until you get to D. Oligosaccharides on cell surfaces allow immune cells to distinguish a person's cells from cells of another organism. True or false? True. How many are on the outside? If you're type O, how many do you have? How many individual monomers are linked together? 3. If you're type O. What if you're type A? You have 4 because you have those 3 and 1 more. What if you're type B? 4. What if you're type AB? You still have 4, but you have 2 different kinds of 4, but you still have 4. So those are all oligosaccharides. Okay, so what do we say? Oh, good. Okay, now remember our blood types. Last question. Read each statement carefully and select the one statement that is false. Select the one statement that is false. And that's correct on the chat. The information for the polysaccharides is stuff you do have to memorize. Yep. Yep. Ten seconds. Okay, so individuals with type O blood can donate blood to anyone, true or false? This one's true. Individuals with type A blood can donate to anyone. That one's false. This one is false. So who can they donate to? Type A can donate to who? Type A. Who else could they donate to? AB. Okay. Individuals with type AB blood can accept blood from anyone. True, they are the universal recipient because they have both A sugars and they have B sugars on the outside, so they can accept from anyone. They're the universal recipient. D, individuals with type A blood have type A markers. That's true. And AB have both A and B, right? So your answer should have been B. Good. Awesome. Y'all did great on clickers today. All right, so let's switch over and go work some problems. No one up there. Okay. All right, so. I get rid of this. Oh well. Okay. So we're going to change gears and we are going to start talking about some forces that occur between molecules, right? And so we're going to start off with gases. Then we go to solids and liquids. So we're starting off with particles that are the farthest away from each other and what happens with them. And then we're going to get to stuff that gets closer together. So the first thing are some gas laws that you have to know. But there's really only two things that you have to remember. What are the two things from the video that you really have to remember? Pivnert and put your peas and vegetables on the table, right? If you can remember those two things, you're going to be just fine for gas laws, okay? All the conversions and stuff like that, that's on the resources page for your exam. So what I really want you to do is when you're doing your homework, to have a copy of that. It's posted on Moodle. Have a copy of it next to you so you know where to go on the sheet to get the information, right? So it's going to make exam time easy because you're going to know where to go. Does that make sense? Okay. So please, please, please use that as you're working these problems. So I went ahead and put up the conversion here at the top, right? But it's 1 ATM is the same thing as 14.7 PSI. Same thing as 760 millimeters mercury, and same thing as 101,325 pascals, right? Okay. So now we're trying to convert these from barometric pressure readings to ATM. Remember how I said dimensional analysis was never going to leave us? It's really never going to leave us. Okay, 101,331. Okay. Oh, put a unit there. A unit would be great. Pascals. Okay. So what conversion should I use? 1,101, 325 pascals, because I want my pascals to cancel out. Whatever unit you're trying to cancel out, you put that unit at the bottom so it cancels out with your original unit. So now, what do I put on top? Yeah, 325, sorry, 325, 325, thank you. Okay, so what do I put on top? 1 ATM, all right. So put it in your calculators, what do you get? What do you get? About what? It's a big long decimal, so we got to figure out how many significant figures we need. How many significant figures can we put? Really, we're given 6 significant figures. You don't use the, typically, you could for this one, you could, but typically we use the significant figures that were given in the measurement, not the significant figures that are in the conversion. Because like sometimes it depends on which periodic table you're looking at, you know, what the atomic mass is going to be, how many significant figures are there. So typically we give pressure in ATM only to 1 sig fig, but technically what we're supposed to do for this question is to give 6 significant figures. So I would accept it either way, but I'm not going to test you on this exam on significant figures. So what does it round to? Let's give it to 1 sig figs, just round to it easily. 1 ATM, right? So Rachel, if you have a question about iClicker questions, send me an email. I'll answer that for you because I've talked about that in class multiple times. Okay, so 762 millimeters of mercury. I want to convert, so I'm going to put millimeters of mercury at the bottom. What's my conversion factor for millimeters of mercury? That always freaks me out, but that stays. But I have 760 millimeters of mercury in 1 ATM. So that's 760 in 1 ATM. So what do I get? 1 ATM, right? If you gave it to 3 sig figs, give it to me in 3 sig figs, because that's what it's really supposed to be based on this. What would you give it to me at? Oh, is it 1.00? Okay. How about C, 14.6 PSI? What's our conversion for PSI? 14.7. Ooh, what's our answer going to be? It's about 1 ATM. But you could give to how many significant figures? If you give me the 3 sig figs, what would it be? 993? So either one's okay. We typically report ATM in 1 sig fig, but based on the question, it really should have been 3. Really should have been 3. Okay. Ooh. Okay. So if we come down, 6.4. Suppose you have the same amount of gas in 2 containers, C and D. Both containers are at the same temperature. Container C is half the size of container D. Which gas is at higher pressure? Explain. What could you go to answer this kind of a question? So what's your gas law? Pivnert, PV is equal to nRT, right? So what are you told? You're told that you're keeping the temperature constant. You're told that, you know, R is a constant. It's the gas constant. ST constant. Is it going to change? No, it's a constant. It's like temperature in this example. And we have the same amount of gas. Amount is moles. So we have the same number of moles. So guess what N is? It's a constant. So the only thing that we're changing are what two variables? Pressure and volume. So if we start out at C, right? C is half the size of container D. What happens when we go from C to D? Our volume goes up. Our volume goes up. So if you can't change anything on this side of the equation at all, and your volume increases, what's going to happen to pressure? We have to equal the same number. Call this number any number you want. Does not matter. It's 50. Doesn't matter. If I increase V, how do I make it still equal to 50? I have to decrease pressure, right? So that's my answer. When I go from C to D, D is going to have lower pressure. You could think about it a different way. If you have a certain container, right, and you double the volume of the container, how often are the particles inside of that container going to strike the wall of the container? They're much more spaced out, right? So they're less likely to strike the walls of the container. That's the definition of pressure. Pressure is defined as the frequency of molecules striking the sides of a container. So if the frequency goes down, the pressure goes down. Okay? All right on that one. So you could explain it either way. It doesn't matter, whichever way makes more sense to you. So you will have lower pressure. You say due to a decrease in collisions with the walls of the container. I'm telling you it's going to be multiple choice on your exam, so, but sometimes I'll have definition-y things, you know, and you'll have to pick the explanation that works. So it's good to understand both. Okay. All right. 7.6. When you swim underwater, the pressure of water pushes against your chest cavity and subsequently reduces the size of your lungs. For every 10 meters below the water surface, the pressure exerted by the water adds 14 psi to the atmospheric pressure. So the total pressure 10 meters below the surface would be 29.4 psi. If we have a lung volume of 7 liters at sea level, what would the volume of your lungs be when you are at the bottom of a pool that is 5 meters deep? It's a lot of information, right? Start picking things out, right? We know that we have a change of conditions. So let's pick out our initial stuff and pick out our final stuff, and then it's going to make a little bit more sense. So tell me about my initial conditions. My pressure is what? My initial conditions are like above water. I'm above water. I have not gone swimming yet. So what's the pressure on my lungs when I haven't gone swimming? You're at sea level. You're at 1 atm, which is another way to say 14.7 psi. Because all the stuff in the problem was given in psi, right? Yeah? Okay. All right. So what was my initial volume? I have a lung volume of 6 liters at sea level, which is atmospheric pressure. That's 1 atm. So 6 liters. Okay. Am I given anything else for initial information? Nope. Okay. Talk to me about final. We're looking for what? For volume, sure. How about pressure? So here it gets kind of complicated, right? All right, so the total pressure 10 meters below the surface, if we're 10 meters below the surface, would be 29.4 psi, right? We want to know only 5 meters deep. So you would have to take what? So if you go 10 meters, that's 29.4 psi. What is it if we only go 5 meters? $14.7 plus what? Well, because we're underwater, right? So we have our 1 ATM plus half, because we're only going halfway down, right? For every 10 meters below the water's surface, the pressure exerted by the water adds 14.7 psi plus 7.234, right? 34? 35? Come on. Okay, doesn't want to erase. 35. Does that make sense? Right? Because if every time we go 10 meters below the surface, the pressure exerted is 14.7 psi. So we're going to have our atmospheric pressure, and then we'll have the water pressure. But we can't write 14.7 again because that's going to be 10 meters. We're only going 5 meters down. So 5 meters down is half of 10. So half of 14.7 is 7.35. Right? Okay, so what do you get for that total? So this is at 5 meters below water. I got 22. What y'all get? Okay, now, I told you the 2 equations you need to remember. What are the 2? You got PIV nert, and what was the other one? PV over T. Where do I get that? It comes from PIV nert, nRT, right? If we assume that the number of moles is the same and R is a constant, we can keep that as a constant, divide by T, and get pressure times volume over T is equal to some constant, right? And so what you can say is my initial conditions must be equal to my final conditions, right? The changes have to be equal. So I can just say these are initial, these are final, but what could I eliminate from this equation for this particular problem? Temperature, I don't have to worry about it. I can just scratch it out. You don't have to remember everybody's individual laws when you're doing these kind of problems. All you have to know is put your peas and vegetables on the table, okay? So our pressure initial was 14.7 psi. Volume is 6 liters. Then our pressure final, 22.0 psi. Our volume final is our unknown. So divide by 22 psi. What do you get for a volume final? I get 4 liters. So the hardest part of that problem was figuring out what's the pressure so far down underwater. So always remember when you're underwater, you have to take that atmospheric pressure and then add to it whatever pressure the water is exerting on the lungs. Okay? That's the tricky part. The rest of it, I think y'all would be able to get no problem. Okay. All right. And y'all did hear on the video that I'm not going to make you convert from Fahrenheit to Celsius to Kelvin. You will have to convert from Celsius to Kelvin, but I'm not going to make you do from Fahrenheit to Celsius and then to Kelvin. Okay, so don't worry about that. All right, 7.8. A gas has a volume of 10 liters at 0 degrees Celsius. What is the final temperature of the gas in Celsius? Be very careful though, you have to make sure that you're in the right units. If its volume increases to 25 liters. All right, so do your initial and final. We're given a volume and we're given a temperature. So my volume initial is what? 10 liters. My temperature initial is 0 degrees Celsius, but I can't leave it that way because you can't do any calculations in Celsius. Plus 273 to give me 273 Kelvin. Now I want to do my final conditions. What's my volume final? 25 liters. My temperature final is unknown. Okay, so I'm always going to start with my peas and vegetables on the table. I just feel like I make less mistakes if I put it all and then just scratch out what I don't need. That's supposed to be final. So what don't I need for this? I don't need pressure, so I can just kind of get rid of that one. So my volume initial was 10 liters. My temperature initial is 273 Kelvin. Volume final is 25 liters. And my temperature final is my unknown. So I'm going to cross multiply. My temperature final is 25 times 273 divided by 10. What do you get? 6, 8. Round to 3 sig figs? 683. And what are my units? Kelvin. But I want it in Celsius. So what do we have to do? If you ever plug things into the Pivnert formula, the R constant is in Kelvin. And so if you don't put it into Kelvin, you will get the wrong answer. Because the constant, the units in the constant are Kelvin. And so the math doesn't work right if you do it in Celsius. It's not completely apparent the way your book shows it because you never actually have to plug into the Pivnert formula. You just kind of use it conceptually. But you do need to put it in Kelvin. Okay. So what do you get for temperature final? Should be like 410. Oh, Celsius, thank you. I was looking at the chat. I saw we had a chat. Would the 10 have to be on top? I cross multiplied. So I took this and put it up here, and then I took the 10 and put it down there, and took this and put it up here. It's just cross multiplying, Alexis. Okay. All right, let's see. Let me clear this. All right. Oh, and one thing I wanted to do this, and I forgot. If you come up here, so what would you expect using Pivnert? Does your answer? We went from what was our final temperature? We went to 200 and what? Oh, 410 degrees Celsius. Okay, so our temperature went up. Can we use Pivnert to check our answer? It's always good to check your answer. So if our volume went from 10 liters to 25 liters, what happened to our volume? Our volume goes up. So if volume goes up, right, what happens to temperature? It also has to go up because the two sides of the equation have to equal one another. So yes, we did our math right. That's a good way to check yourself to make sure that you're doing the math correctly. I always like being able to check. All right, assuming no air can move in or out, what happens to the volume of a hot air balloon as the air is heated? So do your Pib nerd. Okay, no air can move in or out. That means N's a constant, R is a constant. What happens to the volume as air is heated? So what happens to our temperature? So what's going to happen to our volume? It's going to go up. It's going to go up. You could have also said volume will increase because Charles's law tells you that temperature and volume are inversely proportional. But you kind of have to memorize that. And I feel like this is better. Yeah. Okay. All right. Oh, I got to clear that. All right. Oh, this is cool. All right. So y'all know when you're watching TV shows and stuff, you know, and they say bag them, right? What are they doing? They're putting an ambu bag on to help breathe for the person. And there are lots of different valves and stuff inside of this bag that make sure that air is flowing in the correct directions and that kind of stuff. So it's actually kind of complicated. I could put you a link that like describes it all if you're really interested on Moodle. But basically, what's going to happen when you squeeze the bag? If the mouthpiece is over a patient's mouth, right? What's going to happen when you squeeze the bag? What happens to the pressure inside the bag? So as we decrease the volume, pressure's on the same side of the equation, so it has to do the opposite. Pressure has to go up. So how does this help the patient breathe who's not breathing on their own? It's pushing air. They're not breathing, so their muscles aren't working. So this is actually forcing air into the patient's lungs. When they can't do it themselves. And then when you release the bag, air will come out of the person's lungs and come into the bag from a different way. So you're not actually pumping the same air into them every time you squeeze the bag. It's all about a complicated set of valves inside of it. But that's basically what you're doing, is forcing air into their lungs. Okay. Let's skip one now. All right, 7.14. There's a lot of problems in this one. All right, a 100 milliliter bubble of hot gas at 225 degrees Celsius. Oh my goodness. Okay, volume, initial. Let me just start writing some of this. 100 milliliters. It is at a temperature of 225 degrees Celsius and at 1.8 ATM. All right, these are all my initials. Escapes from an active volcano. Ooh. What is the new volume of the bubble outside? So volume final, we don't know. Oops, so I'm just going to put a question mark. Where the temperature final is minus 25 degrees Celsius and the pressure is 0.8 ATM. That's the final. So what do we have to do here? Convert temperature. Plus 273, what do you get? 498. And what do you get down here? Be careful, that's a negative sign. 2 what? 48. Thank you. Okay, so now, remember, peas and vegetables on the table. Peas and vegetables on the table. You're never going to forget that, right? But who can remember Charles's law and Boyle's law and all that? Now, this one, do we need to get rid of anything? No, don't get rid of anything. Okay, so our pressure initial was 1.8 ATM. Now you just have to be careful that everything's in the right units. So our volume is 100 milliliters, which is fine as long as we know that we're going to get an answer in milliliters instead of liters. Temperature initial was 498 Kelvin. Okay, pressure final, 0.8 atm. Volume final, that's our unknown, and 248 Kelvin. If you had left your answer in Celsius, what would you be getting? Some negative values in your answers, and you can't really have negative volume. So it's really important to convert to Kelvin. So what do you get for volume final? Right, you just have to cross multiply 248 and 0.8, right? They cancel. So 248 and 0.8. So what do you get? What do you get? A big long decimal? Well, give me 3 significant figures. We're going to assume, oh no, what do we get? 4, that's 3. Give me 3. 112 milliliters. Right? Does that make sense? PV equal to nRT. Does it make sense? Well, oh, and this one's a little complicated, actually, as I say that. It's complicated because what are you changing? We went from 100 milliliters, we don't know the volume, but our temperature went down and our pressure went down. So our temperature and our pressure go down. So it's kind of hard to figure out what's going to happen to volume when you're looking at multiple things happening. But if your temperature goes down, what should your volume do? It should go up. It should be the opposite, right? And if your pressure goes down, what should your volume do? Go up. So in this case, it's easier to predict, but sometimes when you have all three, it gets kind of complicated. Okay. Phew. Ooh. All right. So we have a cylinder of compressed gas. It is going to be emptied. The pressure inside the cylinder decreases. Explain why this is happening using the ideal gas law. What's the ideal gas law? You've been using it all day. PIV-NERT. It's just fun to say PIV-NERT, right? Okay, so the pressure inside the cylinder decreases. What's changing? So the cylinder empties. It's a cylinder. It's not going to change volume. What else is changing? This is something a little bit new. Our temperature is not going to change. Our R is not going to change. Our volume is not going to change. What do we have left? Moles. N is moles. So our number of moles goes up or down? It goes down, right? You're emptying it. What's the definition of emptying something? Getting rid of it, right? So you started with a bunch and you end with not so much. So the number of moles goes down. So think about that. If your number of particles goes down, what's going to happen to your number of collisions? Collisions with the walls goes down. So what's going to happen to pressure? It's going to tank, right? Pressure is going to go down. That's why you have to be very careful with compressed gas tanks, because they are under extremely high pressure. Extremely high pressure. Okay. Phew, and that was just section 1. Right? This was a long section. Their first and second ones were long. The last 3 aren't so bad. All right. So now we're going to move on to liquids and solids, right? So when we talk about liquids and solids in the body, we're going to talk about physiologically important ones, but you have to understand the basic concepts before we can get into which ones are important to us. So there's one force that happens no matter what molecules you have. What force is going to impact liquids and solids no matter what kind of substance it is? It's London dispersion forces. Is it a bond? It is not a bond. It is not a bond. It is a force. And what are London dispersion forces? Displacement of electrons, but it's temporary. That's the really, really important thing for you to remember. It is a temporary displacement of electrons. So you have temporarily a partial positive and a partial negative side of your molecule. It's not like you have a polar molecule, right? A polar molecule, nothing's happening, and it's polar, and it's got a positive end and a negative end. A London dispersion force is you're basically disrupting the electron cloud. And so they're not uniform all over the molecule anymore. They're clustered to one side or the other side of the molecule. And that's what's giving one side the negative charge and the other side the partial positive. Okay? And they're not full charges, they're partial charges. Okay, so remember it's partial. T-I-A-L, partial. No, I can't spell. Okay. And y'all got this in the video. I'm going to say this again. Tell me about a hydrogen bond. It's not a bond. It is not a bond. If you could start a book of things that drive Dr. B crazy, this would be at the top. It is not a bond. It is an attractive force, just like London forces, just like dipole-dipole interactions. They are not bonds. You are not exchanging electrons. You're not sharing electrons. So that's really, really important for you to understand that they are attractions, okay? So it's an attractive force between a hydrogen that's in a polar bond with another atom that has lone pairs of electrons that are pretty electronegative. So remember, hydrogen bonding is no what? No fun. No fun. Hydrogen bonding is no fun. So you're always looking for a hydrogen in a bond with nitrogen, oxygen, or fluorine. Okay? No fun. All right. Okay, given that only polar molecules can participate as donors in hydrogen bonding, is it true that all polar molecules can be hydrogen bond donors? Explain. So yes or no? No. No, they cannot. Y'all are right. No, they cannot. So to be a hydrogen bond donor, what must happen? Well, you must have, to be a donor, you must have a hydrogen in a bond with what? And it's really a covalent bond, right? Covalent bond with, what did y'all just tell me? No fun. No fun. Nitrogen, oxygen, or fluorine. Should be an or. What if I had is this a polar molecule? polar molecule? Chlorine's going to hog the electrons, right, from carbon. And so you're going to end up pointing at your electronegative things, right? But I don't have a polar bond between carbon and hydrogen, so do I have an overall polarity on this molecule? Absolutely, and it goes in this direction. So is this a polar molecule? Absolutely, this is a polar molecule. Could this molecule participate in hydrogen bonding? No. Do we have a hydrogen participating in a covalent bond with nitrogen, oxygen, or fluorine? No. Okay. So we just proved our point that you guys were correct, right? Okay. And then what are the requirements to be a hydrogen bond acceptor? Let's review this real quick because we're going to have to apply it. It must have a lone pair of electrons on no fun. Okay. So each lone pair, sometimes you'll have an oxygen with two lone pairs. Each lone pair is an acceptor site. Here's another acceptor site. Because you're going to have to distinguish between acceptor sites and donor sites. Okay? All right. Okay, so considering our answers, can water and carbon dioxide form a hydrogen bond, and explain? Let's draw our two molecules. Before you try to answer, draw your molecules. So we know that water looks like this. What should carbon dioxide look like? CO2. So we're going to put carbon in the middle, put oxygen on either side. We need it to be double bonded. What am I missing though? Lone pairs. Each of my oxygens need a lone pair. Okay. Now, can they form a hydrogen bond? Yes, this can be a donor, right? It's a hydrogen that is covalently bound to a no fun, it's an oxygen. Here's another donor, right? Where could I have an acceptor site on carbon dioxide, not on carbon? Any of these hydrogens, oh my goodness, any of these lone pairs on the oxygens could be acceptor sites. So these are acceptor. All of the black ones circled are acceptor sites. Could carbon dioxide have a hydrogen to donate in a hydrogen bond to water? No, there's no hydrogen there. So water has to be the donor and carbon dioxide has to be the acceptor. Okay? So yes. So water is the donor. Water's hydrogen is the donor, right? And then the lone pairs on CO2 can act as acceptor sites. Okay. Name two functional groups that contain ionic charges. Remember I told you all these functional groups weren't going away? They just keep coming back and coming back, don't they? I know. So which ones? There's one that y'all know pretty well. What do we call this? What do we call that? This one is a carboxylic acid. Why carboxylic acid? But is it ionic? No, it's not. But if I lose one thing, I become ionic. If I lose a hydrogen, what do I become? A carboxylate. So this is an ionic charge. It carries a complete positive or negative charge. That's an ionic. Not a partial. It's not that it's polar. It says actually charged. There's another group that's positive. Anybody know? Amines. But they have to be protonated. 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 What does an amine contain? It has an R group that's attached to a. It is a nitrogen. It is a nitrogen. So if I had a nitrogen attached to only one R group and therefore had 3 hydrogens and carried a positive charge, what kind of an amine is this? Primary, secondary, or tertiary? Primary, because it talks about the number of R groups attached. So if I had an R2 and a nitrogen and it was 2 hydrogens and a positive, what's this one? Secondary, and an R3 in H with a plus, this would be tertiary. Okay, so that's carboxylates and amines, protonated amines. All right, so now we're going to start looking at some molecules, finally, right? All right. So identify the strongest attractive force present in the pure substances shown. London dispersion forces, dipole-dipole, hydrogen bonding, ion-dipole, or ionic attractions. Before we do that, I want to ask you one question. Which force is present in all of these molecules? London forces. But why do we not really care about that when we're answering these questions? It's the weakest, it's temporary, it's fleeting, right? So what we're worried about is what is the strongest attractive force. And so we're not listing them all, we're just saying the one that has the biggest impact on the molecule, okay? All right, so look at A. What do we have there? What functional group do we have here? An alcohol? An alcohol? Or hydroxyl? Whichever one you want to call it. What can this do? Because really, what do I have? Really, I have CH3, CH2, 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 bound to an oxygen, bound to a hydrogen. This is really what it is. So what can it participate in? Hydrogen bonding, hydrogen bonding. Hydrogen bonding, because we have a donor here and we have an acceptor here. So if I have multiple ones of these molecules, right, and that's what we're saying, we have a pure substance. So we have lots and lots and lots of these molecules. So one molecule can donate the hydrogen and another molecule can be the acceptor with the oxygen. So you would have like hydrogen, oxygen, and then CH2, 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 CH3, right? And so our hydrogen bond would be basically there. Yeah? Okay. How about KCl? What kind of a molecule is KCl? It's an ionic compound. So what do you really have K plus and Cl minus? But the overall charge of our ionic solid is 0. But you really have all of these cations interspersed with anions, right? That's what an ionic solid is. You have a positive and then a negative, a positive and then a negative, a positive and then a negative, positive and a negative, right? And so if you look at the molecule as a whole, our positives and negatives equal out. And so we write the formula without charges. But if you zoomed in and looked at the actual particles, they would be charged. So what kind of an attractive force is present? This would be ionic, right? Okay. How did they become charged? By swapping electrons, right? By giving and taking electrons. So once the act of the give and take is the bond, but what holds them together is that one is now negative and one is now positive. So it's that attraction, but the bonding is the exchange of the actual electron. I know. All right, CH2Cl. What do we have with this one? Tell me about something that is CH2Cl. What kind of a molecule is that? Polar or non-polar? Polar, absolutely polar, right? If I point at my electronegative atoms, right, I'm going to have an overall dipole moment like that. So this is a polar substance. So what kind of interactions are possible with polar substances? If I wrote an overall dipole moment in red, we call this a dipole-dipole. Because you just have multiple of these individual molecules that orient themselves to where the positive side of one is facing the negative side of the other. And so they're attracted that way because of those partial positives and negatives. How about our last one? Is it hydrogen bonding? I know I've got some lone pairs on here. Is it hydrogen bonding? See some head shaking. Good, I like it. So it can't be hydrogen bonding because we don't have a hydrogen covalently bound to no fun. So it can't be hydrogen bonding. But hydrogen bonding is really just a very strong type of what? Dipole-dipole. Because I know this molecule has a dipole moment. This is the only polar bond in the molecule, so the whole dipole moment looks like this. So I have another molecule right here that's going to interact in a dipole moment right there. So my negative side with the oxygen is going to interact with the partially positive side here on the hydrogen. That's what's going to allow me to attract. Yeah? I feel like we're winding down today. I feel like I have worn y'all out today. I think we're getting close to the end, right? Getting there. Oh no, we still have kind of a few. So what is the strongest attractive force? What did we say? Whoop. This one was dipole-dipole. Did I not write it? Dipole-dipole. Now, we have to be able to draw some hydrogen bonds. All right, CH2O. The first step is always to draw your molecule. And if you don't follow your Lewis structure rules, you might run into some problems. So I want you to take a second. I want you to draw this molecule. CH2O. You draw the molecule. Oh, Rachel, I'm sorry, I didn't see your question. You can send me an email about which one it was and I'll answer it. I'm sorry. Okay, so what did you get for your molecule? Carbon tends to be in the middle, right? So what do we have? Okay, Rachel, gotcha. 2 hydrogens and an oxygen. We need a double bond, that's exactly right. So carbon's now happy, hydrogens are happy. How about oxygen? Not so much. We need 2 lone pairs on our oxygen. Okay. How many hydrogen bonds can this molecule make with water? I need to kind of move it down a little. Oh, but it won't let me. Okay. How many can we make? Let's draw water. Well, let's do this first. On our molecule here, what's going to act as a hydrogen bond donor or acceptor? Our 2 lone pairs can act as acceptors. Can the hydrogens act as donors? No, they're not involved in a covalent bond with no fun. So those can be acceptors. So when I draw my water molecule, I want to draw it to where I have a donor meeting up with an acceptor. So the donor is going to be a hydrogen. So I have a hydrogen, right? I'm going to put my lone pairs on my water. And so I'll end up with, I guess, I don't know, I don't have enough colors. A hydrogen bond here, because this and this, these are donors, right? But is that the only hydrogen bond I can make? No, I have another acceptor, right? So I'm going to draw it up here because I didn't plan very well. Okay, so these 2 are also donors. So I'm going to make another hydrogen bond right there. So how many total hydrogen bonds can this molecule make to water? 2 hydrogen bonds. Okay. All right. Now, we can look at our different substances and we can, if we know their intermolecular forces, we can make predictions about how they're going to behave in solution in certain conditions. So, predict which pure substance will have a lower melting point, baking soda or phenol. Explain your answer. So, let's talk about these 2 molecules. Let's talk about baking soda first. What do you see in this molecule? I see 2 things. I see a polyatomic here. And what is sodium? A metal, right? So I have a positive and I have a negative. So what kind of an interaction occurs inside of this molecule? We have ionic, right? Okay, how about C6H5OH? What's the most that can happen between molecules of this pure substance? What kind of forces are present? I see an OH. That should be a dead giveaway. I can have hydrogen bonding. So tell me which one has a stronger interaction that it can participate in? Our ionic is a stronger interaction, right? So if you have a stronger interaction or more of one particular type of bonding, more of the same kind of interaction, either one of those, what's going to happen to your boiling point or your melting point or any of those? Right? The tighter the interaction is, the harder it's going to be to separate them. So let's talk about melting point first. You have a solid, you're trying to melt it. If they have really strong interactions, is it going to be easy to do? No. So you're going to end up with a high melting point, right? Tell me about a boiling point. In order to go to boil, you got to go from liquid to gas, right? So what's going to happen? You got to break the interactions between the liquid molecules to get to a gaseous phase. So what's going to happen to your vapor, your boiling point? Boiling point is going to increase. And then the last one is vapor pressure. So the more gas you have in the vapor state, the more pressure it's going to exert on the fluid below. So if you have a high boiling point, that means that you don't have a whole lot of particles in that space. So what's going to happen to your vapor pressure? It's going to decrease. If you remember this, you're going to be good. And I know my time is up. But we'll come back to that. So make sure you have that for the last couple of problems for Thursday. We almost got to the end. So close. But there aren't as many problems in the second half of the chapter. All right, y'all have a great rest of your day. Where's my, oh, here's my stuff. Okay, any questions on Zoom?
The second last one, I chose D in the professor's group, and I chose E option. So I don't know why I did that. And the reason I'm telling you is because I got it right, and I was like, I really need those points.
Send me an email and I'm going to see if I can look at it. I don't know what I can do. I don't know what I can do for mine. Send me an email, tell me which one it was, that it was today, and I'll look and see. I don't know what I can do. I have to look.
Thank you.
Yeah.
So this also involved right on.
Okay, wait, let me end this so that, because I don't think anybody had a question right now.